Hello all and warm welcome to Func Prog Sweden. First up, I would like to thank all our recurring viewers. Welcome back to Func Prog Sweden number 7. And to all our new viewers, welcome to the MeetUp Func Prog Sweden. This is the meetup where we explore functional programming and functional programming languages such as Erlang, Haskell, F#, Clojure, Scala, and Elm and more. We have also explored different type of functional stuff like functional thinking, etc. First up, the agenda for today. I'll do a short intro and then we'll head over to functional programming in financial markets by Damián. He will be with us from London. And then we will see Making a Game with Elm and Lamdera by Martin. And he will be with us from the studio here in Stockholm. First up, I would like to thank Odabeat for sponsoring the video stream. Odabeat is a IT consultancy company with offices in Stockholm and Ho Chi Minh, and the company itself is focused on functional programming. If you want to know more about Odabeat, check them out on odabeat.com or head over to social media. Then we have the upcoming schedule for the remaining fall. 10th of October, we will live stream from the office at Kivra in Stockholm. Then the 7th of November, we'll be back with another event here from the studio in Stockholm. And then we'll also plan another event then for December and for January and so forth. If this is your first meetup and you are just watching us on YouTube, head over to MeetUp and join the MeetUp community so you don't miss any of the coming meetups. And of course, make sure to follow us on YouTube. Last but not least, we also have a Discord channel where you can discuss any of the current topics today discussed. Also, one of my colleagues, Robin, is in the Discord server. So if you have any questions, please shoot, and he'll help you to make sure that I'll get them and read them up for the presenter. Yes. That was the questions. And also, if you have questions on YouTube, just shoot them in the YouTube chat, or as I said, head over to the Discord server. With that said, we will start. So let's start. Welcome to Func Prog Sweden, Damián. We'll soon have Damián. Hey, welcome, Damián.
Thank you, Magnus, for inviting me to talk about functional programming in financial markets. So my name is Damián Soriano, and I'm a senior quantitative developer at Standard Chartered. I joined the company in 2017, and I've been working in the same team since then. So the agenda for today, what I would like to do is to talk a little bit about the context of financial markets in general, and a little bit about functional programming in finance. Then I will move to Cortex and Mu, which are our the ecosystem that we produce as a team and the language that we have as a team. And then I will go through some kind of emblematic examples of Cortex and Mu. There's going to be 3 of them. And at the end, I will just draw some conclusions and show you some numbers and some statistics. But before we proceed, I would like to do a bit of a disclaimer. I would like to say that the opinions expressed in this presentation are my own opinions and do not reflect the views of the current or previous employers. Now let's move on and let's start with the context. So what is financial market? Financial market is really more a concept than anything else. It is a place where financial institutions, and that can be large banks or can be like I don't know, other financial institutions, they exchange, so they buy and sell financial products. And these financial products, they are usually contracts, so they are legally binding contracts that the 2 parties enter, and then they contain payoffs, things like exchange of money that can happen in the future, that can happen in the present, exchange of securities that can happen in the future. Some of these exchanges, they are conditional. Sometimes they are optionality, so you can exercise some exchanges or not. So it's kind of a bit. These contracts, they can become extremely complicated, and because all these participants in financial markets, they are buying and selling products. they need a way to actually price these contracts. So they need a way to price these products. In order to price these products, they rely on quantitative analysts that they produce ways of pricing the products. So if you are selling an option to another company or some structured trader to another company, you need to know how much do you need to sell it for. And you don't only need to know the current price, but you also need to know the future price, and more importantly, the exposure that you might get in the future. That means if I agree to sell you, I don't know, like 1 million US dollars against a certain amount of British pounds in the future, then all of the sudden I am exposed to a fluctuation of the exchange rate of these currencies. So I am kind of, that's my exposure in the future. So the quantitative analysts, they are a team of physicists and mathematicians. They basically they work on the models to compute, first of all, the price and the fair price of these contracts, the fair price of these products, but also the exposure of both parties, both counterparties, by taking this position. This sounds a little bit abstract, but like that's kind of like how you would price an option, for example. Now, I would like also to mention that I work in a team called Core Strat, which belongs to a bigger team called MAG, which stands for Modeling Analytic Group. And in MAG, we have Core Strats, that is a team of kind of Haskell developers. We have the quants, the quantitative analysts, and we also have project managers. So all these three teams, they work together as MAG. This is going to be important because I'm going to be talking about Core Strat, which is my team, the quants, and the project managers later. So that is kind of like the role of the quants then is to create the models and implement these models to price and compute the exposure for these financial contracts. And this soon become like the know-how of the bank. So each bank will develop their own models, their own implementations, and this become the competitive advantage of these banks. We are part, as MAG, we are part of something called Front Office, which is a part of financial markets, and that gives us direct access and interaction with trading and structuring functions. So trading and structuring functions, they will be talking with clients, they will be quoting price of the different contracts, and they will have requirements, they will, I don't know, want to try new things, new strategies, so they will engage with us to develop these new strategies for the clients. This is all to accommodate, as I said, fast changing priorities. So a lot of times what traders want to do is like, try something quickly and see how it works. So there's a quick turnaround of, ideas and prototypes. So that's why we sit together. That's why we are so close with trading and structuring. Financial market is quite heavy on financial mathematics. There are a whole branch of mathematics that is developed as part of financial markets, stochastic calculus in particular, but also measure theory. It is heavily used in financial markets. Again, in financial markets, there are a lot of details and a lot of conventions, and millions of details of market conventions is by no means an understatement. If you think about, each currency pair, they will have a different, possible different settlement date. They might have different ways of quoting those currencies. In the commodity space, you have different type of, I don't know, orange juices or different types of petrol or fuel. So there's like a lot of conventions, and all these conventions, they need to be incorporated in the quantitative tools that we build for front office. It is also quite heavy in computation. So there's like a lot of linear algebra and a lot of computation, especially Monte Carlo simulation, that computes like the future path for kind of the underlyings of the different contracts. So it requires a lot of computation. It's very compute intense, the whole financial market in general. Now, there are different lines of business. For example, we have rates, FX, credit, commodity, and equity. And the quantitative analysts, they will be split into these lines of business. But Core Strat, the team that I'm part of, is not necessarily split in business lines. The reason why the quants are split in business lines is because modeling an FX currency or an FX spot is not the same as modeling credit events. So that you will need different mathematics, different tools to model these two things. So that's why they tend to be more split. Whereas in core strat, we can develop applications that work across the whole financial market, that work for different business lines. We also maintain our own compiler, which I'm going to talk a little bit about that later. We have our own CI and DevOps team, and we have like very specific application development. And some of these applications, they are, as I said, used across the whole business line. Finally, project management and model risk, it is shared across different business lines as well. Okay, now let's move on to a little bit about the functional programming in finance. So why is functional programming used in finance at all? There is a significant history of functional programming being used in finance. You can see Barclays using Haskell, Jane Street, a very strong advocate of OCaml, and Standard Chartered also like quite heavily involved in functional programming using Haskell or Mu, which is our internal dialect, Haskell dialect. And then we also have like spreadsheets, right? So spreadsheets are like big programs, and they are like kind of, you can find them everywhere in financial market. And this is spreadsheets. Some people even will say that spreadsheets are functional programs. So this is where all start in Standard Chartered. So we all started with spreadsheet. They are at the core of FP in Standard Chartered. So how did that happen? Well, in 2008, there were all the models built by the quants. They were written in C++, and they were calling those models from Excel spreadsheet through add-in. So in 2008, Lambda was invented to kind of create a bridge between the C++ code and Excel. And this interface was like a pure interface, support high order polymorphism, parametric polymorphism. Sorry, high order functions and parametric polymorphism. Then Lambda started becoming like extremely popular. So a lot of traders will go and use Lambda in the spreadsheet. But it wasn't a fully fledged programming language. So it was like more like a kind of an experiment or a binding between Excel and C++. So you will see this massive spreadsheet, with a lot of codes, and it was really hard to reuse. There was like no concept of module or anything. So at some point, people start thinking, okay, maybe we should invent something that is more like a programming language instead of this Lambda prototype. Haskell was a very strong candidate back then, but the integration between C++ and Excel was not, strong enough. So it was decided maybe to find a compromise there. Lambda also had the ability to serialize all values. So everything can be serialized and over and deserialized on the other side. So these two things, they didn't play well with Haskell. So as a compromise, Mu was created. Mu will keep the kind of Haskell syntax and kind of semantics to some degree, and the look and feel, and it will also work very well with the current ecosystem that Lambda was supporting. So that is how Mu came into existence at Standard Chartered. Now, let's talk about Cortex, which is Mu is kind of part of Cortex. So I want you to have like a bit of an understanding of what Cortex is. So Cortex is the main pricing library in financial market. Cortex is a lot of things. It is kind of the entire ecosystem that we as Mag develop. It contains various of the libraries for quantitative finance, all the modeling built by the quants. It is shipped with Cortex. The Mu compiler is also shipped in Cortex, so it is containing Cortex. All the C++, .NET, Java, and Excel interface, they are also built in Cortex. We have a lot of GUI applications, and you can see over there on the right, this is like a screenshot of the home app, which contains links to other applications that are built using Mu. This is like a desktop application actually. Cortex can be installed, and it is installed indeed in a lot of the traders' machines and in our machines as well. So you can use it as desktop application, but we also deploy Cortex on different servers and to run like different server-side components for different things like intraday risk calculations or stuff like that. It is also built, tested every day, and we do have a release, an automatic release every day. So if traders want to update to the latest NAGLI, they can go and download the latest NAGLI and install to get the latest updates. People can also decide to use the latest NAGLI to deploy into servers. So all this is kind of what Cortex is. Now I wanted to stop for a second and show you an example of a script that computes something called interest rate delta and send it over through an email. So this piece of code is mu, and what it does is a quite compact piece of work. So what it does, it start by connecting to an external service, which is called TDS, and TDS is where our trades are. So we basically go and create a connection to TDS. We get the current date, and then we try to fetch, or actually we fetch all the trades that belong to portfolio A and B and that are live trade. So that line over there that you can see that says get trades, what it does is just go to the external server, perform this query on the external server, and return all the trades that belong to portfolio A and B and that are live trades. Then what we do is we call something called quick risk. With a set of options, we specify these are the trade population that I want you to take into consideration, and I want you to compute this thing called IR delta. So IR delta is the sensitivity of those trades with respect to changes on interest rate. And I'm sure that everyone is aware, about the interest rates becoming a big topic lately. So it is kind of quite important. So we wanted to know how sensitive are we to that change. And what we get is like as a result, we get the actual result that will be the risk scenario being computed, but we also get the errors. What we do after is we save the results, and then finally we send an email with the results. And the way that we send an email is we specify recipient, we specify from email address, we also specify subject, we do like a little bit of body, like you can see, like it says number of trades, number of errors, and we send the IR delta as an attachment in the email. So you can see that this very concise piece of code is already computing something quite interesting, right? So you just like get your live exposure in portfolio A and B, and you receive, the exposure that you have on changes in interest rate delta. And if you are a trader that trades on interest rates, then this is something very useful because you can see your exposure to changes in interest rates. And it's very compact. Now, there is very little here that can give you a hint that this is not actually Haskell. So if you look at this, it's like, it's just like, it's almost like pure Haskell, really. But actually, it's not Haskell. This is mu. And even though Haskell and mu, they are like very similar, they are not the same. There are some key difference between Haskell and mu. Mu, first of all, is a whole program compiler. That means that separate compilation is not possible. That means that every time that you need to compile a program, you need to compile all the dependencies. This has some advantages and disadvantages. The main disadvantage is that every time that you need to compile a program that imports a lot of stuff, then the compilation time will be much higher. And as a result, we do experience compilation times longer than you would expect in normal Haskell. But on the plus side, because it's a whole program compiler, it kind of contains all the instances of all the function call, for example. So if you define a function that is called only once in the whole program, then mu actually say, okay, actually you're defining a function that has all these parameters, but you are using this function only one time. So the compiler can be extremely aggressive at optimizing the code. Because it knows everything that needs to be known about all the uses of all the functions and type classes and everything. So it can perform very aggressive optimizations. Mu compiles to bytecode, which runs on a very small interpreter instead of compiling directly to binary. That's another key difference. Mu, this is like kind of a big one, I guess, for a lot of Haskeller. So Mu has like a strict runtime, but lazy semantics. And this is interesting because we want Haskell developers to, be comfortable with, the experience in using Haskell. So this line of code from maybe undefined just unit, every Haskell developer will say, okay, this obviously returns unit. Because like you don't need to evaluate and define. But if this will be strict, then before calling from maybe undefined, we'll need to evaluate it, and that will raise an exception. So we do annotate a lot of functions to maintain the lazy semantic that Haskell have, but we are Mu indeed it has a strict runtime, which is like has its own problems, but it's also has its own advantages. Strings are native, so they are implemented in C++. In fact, Mu doesn't have a char data type. So yeah, this is like also a big difference between Mu and Haskell. There is no foreign function interface. Like C++ can call Mu almost natively, or actually natively, and C++ and the same thing the other way around. Mu functions, they are exposed into something called object-side functions that can be called from C++. So there is this kind of, you can call in Mu, you can call C++ and C++ can call Mu, and you don't see the difference if you are working in Mu. This is another big one, especially for Haskell developers, and recursion is discouraged. That means that this like explicit recursion is disabled by default. So if you try to define a recursive function, the Mu compiler will complain. You have a pragma to enable recursion, but it is discouraged, so it is disabled by default. It has some positive effect on the runtime implementation, and to be honest, I'm surprised that it's rarely needed. So less than 4% of the modules that we have, they do enable this recursion pragma. And in fact, I'm sure that a lot of these modules that can be rewritten without using explicit recursion. And as a consequence, we obviously have like some recursion primitive that we rely on when we define functions. But yeah, this is also like quite shocking that you actually, in a lot of cases, you don't really need explicit recursion. The extensions, because we are not using GAC, there's like a lot of or plain Haskell, there are like a lot of extensions that we don't have. We don't have existentials, GADT, or rank 2 or rank-n types. Yeah, so these are like kind of like some of the things that you don't get because you maintain your own compiler. The deserialization and serialization is supported for almost every type or everything in Mu. So you can actually serialize everything, send it over, and then deserialize it on the other side, which is extremely useful in the environment that we operate. And finally, we tend to use relations instead of lists quite a lot. And when I say relation, I'm talking about kind of relational algebra. You can think of these as kind of data frames in Python, so to say. So they're like heavily optimized for computation. So we do rely a lot on relations instead of plain list. So these are like kind of the key differences between Mu and Haskell. The syntax is almost identical. Now, I would like to describe a little bit how the Mu compiler works. So we start, this is the current status of things, right? So we start with the Mu source, the Mu compiler frontend, pick up the Mu source, pass it, and generate something called Mu exp, which if you are familiar with GAC, that will be core. So it will be very similar to core. Then there's a lot of optimizations happening at the Mu exp level. And when those optimizations take place, then the Mu compiler backend compile that into bytecode. And bytecode is what we use to run on the interpreter. Now, we are currently working on moving from this to this. And this is going to be the future. So what we wanted to do is to use the GAC frontend. That means that all the passing and maintaining all the stuff, we don't need to do it anymore. Still to be seen if we have like GAC source or GAC Mu source. So it's not clear if we can maintain just GAC source. Mu has its own syntax stuff. But the idea is to use the GAC frontend to convert into GAC Mu source code into GAC core. And then we will have a small component that converts from GAC core into MuExp, and then MuExp will be taken care of by the Mu compiler backend. So this will bring us closer to GAC and to kind of more traditional Haskell or Haskell that you can see outside standard charter. But we also don't need to maintain the Mu compiler frontend anymore. We will be relying on the GAC frontend. They are as part of the team of Core Strat working exclusively on this new pipeline. Right, now I wanted to move to some examples, some emblematic examples that we have in Cortex and in Mu. So I wanted to start talking about our widget library. So as I said before, we do build a lot of GUI applications for traders. So how do we do this? Well, we rely on Windows Presentation Foundation for building GUIs, and this is basically a Windows native thing. So Windows support, building GUI applications through Windows Presentation Foundation, and we use that to build GUI applications. The plain library is called widget, and widget has like kind of like bindings to different parts of Windows Presentation Foundation. There is a more recent and more modern widget library that is called virtual widget that implements something that like the Elm architecture. And this is interesting because the next speaker, I'm sure that he will have so much to say about this. But it's very useful because for us it separates the UI part with the business logic. I'll show you an example of these two libraries shortly. Both libraries, they kind of support also HTML and JavaScript backend. So we can, Cortex can be installed in a Windows desktop, and that's how a lot of people use Cortex. But we also deploy Cortex into servers, and we run what is called widget server. So you can go to your browser, point to the server address, and then you will see exactly the same as you will see in the desktop application. And I think that this is like pretty cool that you can actually you define your own the same kind of code base, and then you can render to HTML, JavaScript, and desktop application using Windows Presentation Foundation. And Mu runs on Windows and Linux, so we can deploy on both type of services. Now I'd like to move to this like very small example, and it's just to illustrate how the widget applications work and the two libraries. On the bottom left, you will see like a very small example, and what it does, it's just like a kind of a text box that accepts integers and a button that you can click and increments the counter by 1. So the status of the whole application will be just an integer, really. That's the integer that you display, and that's the integer that you update or you increment by 1. Now, on the left-hand side, on the top part, you see this application written using plain widget or native widget library. Now we start by creating an int box. This is a text box that can contain only ints. The initial value is 0. We create a button, and when there is an event on the button, that means that the button is clicked. We go and modify the input and increment it by 1. And finally, we return the input next to the button. Now you can clearly see here that input is used for both maintaining the status of the application, but also as a UI component, right? So when input is used in modifying the state and also return as a UI component. This is not the case on the other using the other library using virtual widget. It is a bit more verbose, but it is for bigger application, it is much easier to understand. So what you need to do is to define first of all a model, and the model in this case is going to be an integer. You define two types of messages. The messages are someone changed the counter. That is happens when someone goes and change the actual value of the counter, or someone click. And then you need to define an update function. The role of the update function is to say, okay, given I see this message being raised, I have this model, what is the next model? So it's basically provide model transition on messages. So you basically say, okay, if someone changed the value, then this is a new value. Otherwise, just increment the value. And then the view define how this is displayed, and you say, okay, I'm gonna display an inbox that contains ID, and you say like, because ID is exactly the type of the model, you say like, just display the integer. But if the inbox change, raise the on change message. and then put this next to a button that when it's clicked, raise a click message, and we will display a label saying count. And then the main function that basically put these two things together, or put all of these together. But as a result, you get the same application. Okay, so this is like just to show you an example of the two libraries that we have, and the incredible thing is that both of these two things you can either display as a desktop application or in the widget server. This is another example, but I'm gonna skip it. You will find it in the slides. I will distribute later. It's a more convoluted example, but it's still quite simple. It's just converting Fahrenheit to Celsius and the other way around. Now this is how you will see the two backends that we have. One, the smallest one is Cortex display as a desktop application, and the other one you see that that is like a browser connecting to, in this case, a local host. So that's like spawning the widget server locally, and then you see that the view is exactly the same. So we get like both renderings, and clicking and everything works exactly the same way. So these are the two backends that we have for displaying widgets. Now, the second example that I want to show you is QuickRisk. And QuickRisk is an API that we have to access all the pricing libraries. So all the models that are built by the quants, those models, they are exposed using QuickRisk. So QuickRisk is one of the most used kind of APIs that we have in Standard Chartered, and it allows you to do like an incredible amount of stuff. It generates kind of a workflow depending on the inputs or the outputs that you specified. For example, the typical use case is, say, you tell QuickRisk, go and fetch some trades and give me the results. And then QuickRisk will compute something like this. It will say, okay, I need to go fetch the trades, then I need to compute the results. But to compute the results, I need the price and the attributes. To get the price, I need the market, because the price of the trades that will depend on the market. So I need to compute the market. What do I need to compute the market? I just need the trades. Okay, so it creates this kind of graph that display the dependencies between the nodes, and QuickRisk knows that it needs to go from trades to results. And this is all like created. This is like a simplistic example. I will show a more complicated example. This is a simplified view of what QuickRisk creates. Now, the cool thing is that sometimes you don't want to compute the results, and the results will be something like I said before, like a risk result that will be like, for example, interest rate delta. Maybe you only want to compute the price of the trades, and for the price of the trades you actually don't need the attributes, you just need the market, and you can specify this in QuickRisk with only this line, which I think is like incredible. But like what it does, it produces this other graph which says, okay, you start with a trade, and the trade is in yellow because instead of QuickRisk going and fetching the trades, you are just like providing the trades for QuickRisk. And then I need to compute the market, and then the result is the price. So it all of a sudden realize, okay, this is a smaller computational graph that I need to compute. And the cool thing about QuickRisk is that what the result or the output of QuickRisk is specified as a result of the type of the call, which is it's hard to explain, but basically what I mean is like you see a type annotation there, which is like IO price. So that is the type of the complete computation of QuickRisk. So if instead of putting IO type there, you will put IO result, then QuickRisk will figure out that actually it needs to go and compute results as well. And if you put IO price at the tuple of price and results, then QuickRisk figure out that it needs to give you the price and results. I think that the API of QuickRisk is pretty cool in that regard. But yeah, so basically this is how QuickRisk kind of works. The computational graph, it is encoded in an ADT that I will show briefly. So it's like an abstract data type that encodes all the computation. Now, the execution of the graph is separated from building the graph. So you build the graph, you have all your nodes, you have all the links, you say, okay, for this I need that, and for this I need that. But then how you evaluate this graph, you can potentially evaluate some things in parallel. Market and attributes, they can be evaluated in parallel because there's no dependency between them except for trades, obviously. But once you have the trade, you can spawn these two computations separately. So you can have like on one hand, we have like QuickRIS building the graph, but you can also tell QuickRIS how to evaluate the graph. And you can evaluate it sequentially, you can evaluate it in parallel, you can evaluate it out of process if you want to. So there's like a lot of strategies that are support in evaluating these this graph. The nodes get shared if they are like computing the same thing. So QuickRIS is quite clever in that. So it doesn't waste computational power. It reuses the nodes when it can. And this is the kind of QuickRIS API. So this is the internal QuickRIS API. It is kind of a simplified version of the QuickRIS API. So you can compute a pure function. You can compute an application. So if you depend on some work, you can compute a new work, or you can compute a something on I/O. So those kind of like a simplified version of QuickRIS. You can see that work underscore is not particularly type safe, but this is fine because this is actually not exposed to the user. The user can only use the functions to create work. So and we have like over there a function type that actually tells you the type of things. So you carry the type information around. So you can say, okay, I can compute this value A. It is a pure work, and then you can link these things together. So these are kind of an example of sorry, not an example. This is actually the API of QuickRIS. Right. And then the last thing that I want to show you as an example is something called Shepherd. And Shepherd is what we use to manage our workflow and to schedule jobs. It is fully implemented in Mu. It is quite robust in the sense that if you have like a node that fail, Shepherd will kind of, there's like different things that you can tell Shepherd. You can say, okay, just like send an email to someone if this node fail, or but it catches the exception like kind of locally. This will become more obvious in my next slide. It does manage that, so you can, because it's about like managing workflows, you can define, like QuickRIS, you can define different nodes that they can be linked together, and it provided type interface to link those things together. So if you have like a job that computes, I don't know, 10 numbers, and then you have like another job that needs those 10 numbers, Shepherd will provide a type API for this. So if you, I don't know, like in the future, instead of returning 10 numbers, you return 11 numbers, then you have like a type error. It supports very flexible schedules, a little bit like cron. So you can say, okay, run this workflow daily, hourly, or you can say, okay, every Friday at 2 p.m. on New York time. It has support on localized time. You can also specify what are the resources that your job needs and what are the resources that you have available on your computer, and Shepherd will only schedule jobs when there are enough resources to be scheduled. So it will block all the jobs until resources became available, and then we start scheduling jobs as resources become available. It supports multiple Cortex version, and this is extremely useful when doing deployments. So for example, you can think of, I don't know, you have like a new Cortex version you want to deploy to the server, and then you wanted to test it before you move production to that new version, and then you basically run like a test run, see if everything works, and then you just move the production batch to use the new Cortex version. And we do this all the time, right? And if something goes wrong, you can always roll back to the previous version. So it's like deploying, upgrading, and rolling back is extremely easy because Shepherd support multiple Cortex versions. You can use Shepherd as a library. That means that you can schedule workflows, entirely workflows from a script or a program, or you can use it as a client-server solution. You can open a Shepherd GUI and then connect to your local server if you want to run things on your computer, or to a remote server, and then you can spawn calculations remotely. You can even spawn calculations remotely if you use Shepherd as a library. So you can say, I want to run all this workflow on a remote machine. This is extremely powerful. We do use Shepherd quite a lot. The other thing is, like, this is a little bit for like when a lot of traders that will have their own workflows running on their computers. So Shepherd doesn't require like something running all the time. So we have ways to spawn all these runs at system boot. So when a trader restart the computer, then Shepard, the Shepard schedule will start automatically, and then all the jobs that will run. This is to prevent, I don't know, if the computer gets rebooted over the weekend or something like that, or something crashed, then the trader will know that the Shepard jobs that they define, they will run anyway. And this is the kind of how Shepard look like. So this is the Shepard GUI, and this is kind of a normal workflow that we will have. You can see that it all starts with trades. Like a lot of the workflows, they start with trades, right? So that's kind of the input for almost everything. And then at the far end, you see something called dataset. Now, dataset is the final results that we want to produce. In green, you can see all the jobs that are, well, first of all the arrows are like, define the dependencies between one job and the other. The green nodes, they are the nodes that already finished computing something. The yellow and the purple need further inputs. The blue one is the only one that is running at the moment. The dark red is something that failed, and the light red is something that is blocked. So when this when this workflow finish being executed, then dataset will become blocked. Fail. And that means that you fail your computation. Now let's imagine that this whole workflow takes like 5 hours to compute. You don't want to run the whole thing again. Maybe, I don't know, maybe attribute internal, which is the failed job, it couldn't connect to a server. So what you can do is you can go to that node, you can say restart, and Shepard will say, oh, actually, I don't need to compute all the other things. I just need to compute this and all this dependency. And maybe that is like, I don't know, like 5 seconds. And then you save a lot of computation power because Shepard keep track of all the dependencies and all the information that these nodes produce. So this is pretty cool as well. I mean, I think that, you can actually, it's kind of an incremental computation thingy. So you just compute a bunch of stuff, Shepard save these things for you, and then you just can, replay only the part that failed. And this is all the examples that I want to show you. Now I'm going to move to conclusions, and I want to show you some, like, only a couple of statistics for you to know a little bit about the context here at Standard Chartered. First of all, like the whole modeling analytic group, we are like more than 100 people working there. So that would be both quants, project managers, and core strat. About a third of the MAC team will be core strat. That is the team that I work on, and again, like this would be like kind of mainly Haskell developers. We have 6 million lines of code of MeetUp, which is quite impressive. 500,000 of lines written in Haskell, and less than 2 million lines of C++. These are some statistics about like the contributors over the past 15 years. So the project's been live for quite a long time. So we have like more than 700 contributors over those 15 years, and a lot of commits as well. And only in the first half of this year, we did merge 3,800 pull requests into our master branch, which is like, that shows the amount of work that is going on in Cortex. There are hundreds of applications that we maintain, as I already said, and some of the most popular applications, they have more than 1,000 unique users per month, which is quite a lot if you think about, like, these are internal applications only. This displays the growth of lines of code in different languages over time. You can see how Mu, ramp up a lot, and then it's keep being very active. And then you see C++ and Haskell being kind of more plateauing. So C++ is, you can see that is used less intensively than Mu. Like a lot of the development now is happening in Mu. And by the way, this graph was produced by one of our applications, which produce graphs. And then we can have like this kind of really cool interface that display graph in the applications. These also show the contributors over per month and the commits per month over since 2008. There's nothing significant about this graph. I think that is pretty much what you would expect. And finally, as the business grows, we also grow. So we always are looking for Haskell developers. So if you feel like you wanted to apply for any of the positions, this is how you will find our positions. Or you can send an email to coursestratroles@sc.com. this information will be shared on the slides as well, so you can just follow these instructions to find the open positions. And that will be all. So thank you for your time, and thank you, Magnus, for letting me speak here. And I'm happy to take any questions that you might have regarding the presentation.
Thank you very much. Very interesting presentation. Thank you. We had one guy had a question in the chat, but it was answered by another guy in the chat. I kind of was on the way to ask you, and then another friendly person also saw the same thing as I saw in the chat. Yes. We have one question that came in the beginning of the presentation. I didn't want to interrupt you then, but is this the kind of work you've done, is it based on like what Simon Peyton-Jones, Eber, and Stewart have done? You know, it's
like what, in terms of the contract language?
Yeah, I guess that's what's meant.
Yeah. So so I think that we have like a contract language internally. I think that is based on the Simon Peyton-Jones paper. But it's been expanded obviously, and it does change all the time. But yeah, we have some work on that, on the contract languages based on Simon Peyton-Jones paper. Yeah.
Yes, people are saying thank you very much in the chat. However, I have some more questions. First up, I usually ask this to every presenter, is like, how did you come into Haskell, and how did you come into functional programming?
Right. So I think that, well, I learned Haskell in university. I am from Argentina, from a city called Rosario, and the computer science course there, I don't know, for some reason they teach you Haskell as the first language. It is kind of like, I don't know, I don't know how the curricula got in place, to be honest, but yeah, there's like a lot of interest in functional programming in that particular course. The course is called, I think it's the way to translate is licentiate in computer science. It's like a 5-year course. Sometimes it's equivalent to kind of a master, but I don't know, it's like a different, I think it's like the old way in Europe that you will have like careers or something like that. Anyway, so I studied there, and then I saw like a lot of Haskell and everything. We go into, type dependencies and type dependent languages, Cog in particular. So it's very kind of like computer science traditional curricula. And then you finish university, and then you start looking for jobs, and there's not a lot of functional programming jobs out there, especially not in Argentina. And so I then start working on other for companies in different languages. I did some work on Java and C++, and then a little bit on C#. And then for a while I did like mainly Python. But even in the company that I used to work before, we were doing like mainly Python. There was like some interest in Haskell in particular, so we start building some microservices in Haskell. A little bit at the beginning, like a prototype, and then it started to pick up like a lot of traction. So a lot of developers, they become really eager. So we start like running some kind of Haskell clubs, or I don't know how you call it, like every day, like sharing experience. And then at some point, I really wanted to take the next step and use Haskell for real. So that's when I knew that a standard charter it was used, and I came across like a presentation from, I think it was Martin Stewart back then, which was working for standard charter. He also wrote a book about Haskell, and I thought like, yeah, this sounds like really cool. So I just applied. I studied a little bit before because I was a little bit rusty on the edges when it came to Haskell, and then I've been doing Haskell professionally for the last 6 years. Yeah, so that's kind of a little bit of my history behind FP.
Cool. I have a question in the chat. They say functional languages has efficiency problem on memory consumption during runtime. Is this true?
I don't think that that's a problem that is particularly for functional programming languages. I think that you can have like leaks on a lot of languages. Mu is a little bit, because it's strict, I think it's like understanding possible memory leaks and problems in memory is a little bit easier than other languages that are lazy, I think. But like I don't know, like when we find these kind of issues, then we try to solve it, and most of the time we can solve them. But I remember like having similar issues with memory as well, memory allocation as well in Python and other languages. So I don't know. I need to see more like concrete evidence for this. I'm not convinced that this is a specifically functional programming problem.
One more question. Does Mu have any totality checking? Any plans to implement it?
Right. No, and I don't think that there's any plan to implement it as I am aware.
Okay. I have another question, but I guess, I see Mu. I guess Mu is kind of open source, I guess, on GitHub.
No, that's like actually not the case. Mu is a proprietary. No, it's our own compiler, so it's not. Very little that we do is open source, if anything, actually. And this is because Mu is so intertwined with Cortex, and Cortex is kind of the kind of intellectual property of the bank. So it's really, first of all, it's hard to separate them, and also I don't know if there's going to be much value in having Mu per se without all the other Cortex stuff.
Okay.
So no, it's not open source, unfortunately. Yeah, but you can use Haskell. That's a very good proxy. It's almost the same. So.
I understand. Yes. Then next question: does Standard Chartered have any issues recruiting Haskell people?
This is a very good question, actually, and we have no problem hiring people. So we did manage to grow like quite fast, and we received like a lot of Haskell developers. We do interview a lot of people, and we found no problem recruiting Haskell developers at all. If anything, maybe I don't know. I don't want to say that it's easier but it's really easy to find like Haskell developers. I would say we never had any problem that we couldn't fit positions. We actually reject like a lot of candidates because they are, I don't know, maybe they are not at the level that we are like we are hiring, or we hire at different levels, so it depends on our expectations. So we want to be fair with the candidates as well. So we don't want to hire someone that is not going to be able to function well in the role that they're hired for. So we need to be careful with that, but we never had any issue hiring at different levels. Even at senior levels, we do manage to hire quite successfully.
Interesting. Yeah, this is my how should I put it? This is my.
I think it's a myth, right? It's just like, I think like it's a bit of a myth, right? So finding Haskell developers is not easy. Actually, it's not. That's not the case.
No, I agree. I'll tell everyone. As you stated in your presentation, I think when you started, we'll share around the presentation for anyone that wants to, run through the slides again. We'll share it. And again, thank you very much, Damián, for your presentation. Thank you very much.
Thank you for inviting me. Thank you.
You're welcome. And with that, we will head over to our next presentation. Welcome, Martin.
Thank you.
Yes.
Glad to be here again.
Yeah. Second time around. You were like 1.5 years ago, I think you were here.
About that, yeah.
Yeah, exactly. And today you're going to present making a game in Elm and Lamdera. Actually, your own game that you made.
My own game, yep.
Yes, I think it's very cool. I've seen some of the slides already. It's very fun. For us born in the late 70s, this is a game that will talk to you, I would say. With that, I'll head over to you. I'll hand it over to you, Martin.
Thank you.
Hit it away.
Yeah. So as mentioned, the title is Making a Game. Excuse me. Making a Game in Elm and Lamdera, and I'm Martin Stewart. So, sorry, just lining up the slides. Town Collab is the name of it. It's a multiplayer town building game. So the idea is you and some friends can hop on. It's like a big shared infinite canvas. And you can place down houses, trees, roads, railroads. And there's no real objective to it. There's no real win or lose conditions. You could think of it in SimCity in that regard. You just build for the sake of building. It's made using Elm and Lamdera. Elm, perhaps you're familiar with. It's a functional programming language designed to be simple. Its own marketing term refers to it as delightful. And it's designed for making web apps and websites. Lamdera is a framework that uses Elm so that you can write Elm both on the front end and the back end. So as I just mentioned, Elm is intended for the making the website. Lamdera is a framework that helps you write back-end code with Elm also. On top of that, Lamdera helps with, it makes migrations type safe, it makes communication between the front end and back end type safe. You don't need to worry about how you're going to do hosting or deployment. Lamdera takes care of it for you. It's very handy. And as some background to this, this game, Town Collab, I tried to make it, we'll say 4 years ago, plus or minus a year. I tried to make it, but I used Elm on the front end, of course, and C# on the back end. I'm not giving this presentation as of 3 years ago because that version went nowhere, because the issue I ran into was that having two separate languages, one for the front end, a different one for the back end, is that I end up rewriting the game logic twice, because the server needs to run the same game logic to keep things in sync. But with Lamdera, that problem's solved. Elm on both spots. This game is inspired by an old children's game called Lego Loco, which maybe some of you have heard of. Maybe I'm the only one who enjoyed it as a kid. You can think of it as this game, but no multiplayer. You're stuck to a... your world is the size of your screen, and there's no undo. Those are things that are hard to go back to, even if I have a lot of nostalgia for it. So I wanted to make my own version of that. Okay, so that's enough describing this. What does it actually look like? Well, as you might have already guessed, we're looking at it now. This is the website, the game. Yeah, and you know, you can place down houses, trees, flowers, roads. There's a train looping around. But in this talk then, I would like to connect this a bit with functional programming because, you know, given that I wrote this in Elm, there's a bit of functional programming that comes in how I designed it. So two topics in particular I'd like to talk about is how networking is handled, how networking is handled. So that would be the communication between the front end and back end, how multiple players can stay in sync. There's not race conditions, for instance. And the other thing is how the graphics are drawn. WebGL is used in this case, but how that's done is something I will go into detail. All right, networking. So there's two systems involved here. One's responsible for placing tiles. So by placing tiles, I mean like placing the buildings or placing the roads. And the other system is responsible for moving trains and cursors. So by cursor, here's my cursor. If anyone else was playing right now, they would also be able to see my cursor moving around. And likewise for trains, of course, everyone can see the train moving. So starting with placing tiles then. The best way I have to describe it is to use an analogy with Git. So hopefully everyone uses Git as their versioning control, but this might apply to other version control systems as well. So in this view here, on the left we have Git history. So you can imagine here we're starting off with, we have our main branch, and first one person placed flowers. So we're going to call this the flower commit. And then someone placed a rock. That's our rock commit. And on the right here, inside this little black fence, that is what we're imagining as what we see within the web app. So we're on the main branch, we have the latest commit, and because of that, we see the flowers and the rock in our little fenced off view. Okay, so let's suppose now we have a race condition. Oh no. On the main branch, someone else has merged in their commit. They've added the bus stop. And on our local branch, we've added a elm tree. So the problem now is these two things have been placed at the same time. And worse still, they've been placed at the same spot. So right now we see the elm tree. That might hint to how this conflict gets resolved. But let me explain what happens. So as I just said, the bus stop gets placed, the tree gets placed. They're in the same spot. So locally, we have our own branch, and the local branch contains all of the changes that the server has not confirmed that it has yet. So we've just placed down a tree, and we don't want to wait for the server to confirm our change. We want to see it immediately at our end, because otherwise, the UI feels unresponsive if you have like 500 milliseconds delay between clicking and seeing the object placed. So local branch, those are our changes, only we see them. The main branch, those are commits that have been confirmed by the server, everyone sees them. So in this case, we have the bus stop, we have the tree. We only see the tree at the moment because that's what we placed. And so the next step then is what I would refer to as a rebase. We get the bus stop commit from the server, and the way we handle it is we take our local branch and we rebase it on the latest main commit. So that would mean then we take our tree and we rebase it from the bus stop. So what's happened is we have this flower that got placed, we have the stone that got placed, then the bus stop, then the tree, in that order. So I'm going to do a little instant replay now to make it clearer why we see what we see in the fenced off area. Specifically, you might have noticed what happened to the rock. So I'm going to just enable the UI here for a moment. And so if we start from scratch here in our view, first the flower showed up, then the rock showed up, then the bus stop showed up, and you notice the bus stop knocked away the rock just because of how it was placed. And then our tree got placed, and it knocked away the bus stop. So this is how conflicts are handled. Let me just hide the UI now. This is how conflicts are handled within the game, is that each change is treated like a commit. Each action is treated like a commit. And while you're waiting for your commit to be confirmed by the server, you have it on a local branch. And if you get in anyone else's changes, then you take all your local changes and you replay them from the latest main branch, or the latest main commit. So here at the end then, we see that now the server has confirmed that we placed the elm tree. So that's on the main branch, and our local branch is empty because we don't have any outstanding commits. And so we end up with just the flower and the tree. And here I've been just talking about placing items, but actually this is more general than that. For example, if we were to hit Control-Z, undo or change, that would be a new commit, the undo commit. So that would get placed on top of the existing history, and then everyone else would be notified when it's broadcast to them that, okay, this user undid their tree placement. And so the tree would be removed for everyone. And all of this would be handled in a way that's race condition free. There's no risk of the order in messages causing people to see different versions of our tiles. Moving on. So the trains and cursors, in contrast, let me just slide up the slide. There we go. For trains and cursors, there's a different system. Here we're only interested in the latest cursor position or the latest position of a train. We're not interested in the history of like who placed what in what order, because at the end of the day it doesn't matter. If I move my cursor around, it doesn't matter what order event other cursors were moved in, because my cursor is just its own position. It doesn't, it's not affected by anyone else's cursor position. In addition to that, oh, excuse me, I should have mentioned earlier, with the other system, it's very important that when you are replaying events, so here, let me go back up here. When we rebase and we need to replay events to figure out where all the tiles are sitting, it's very important that it's consistent in how you end up in your final state. Like every commit, every change should have the same effect. You might, as functional programmers, we think, well, obviously pure functions. And yeah, pure functions make this very easy. The fact that we're working with functional programming means, well, I should say, Elm is a pure functional language. So all the functions in Elm are pure functions. No exceptions to that, which means there's no way to accidentally screw this up, which is really nice because debugging multiplayer race conditions is one of the hardest things you can do. So there's certainly an advantage there in contrast to other functional programming languages that are, we say, more flexible, that have escape hatches. Anyway, yeah, so for trains and cursors, we don't need the complexity of handling race conditions because it doesn't matter. For trains, we're just broadcasting, or the server, I should say, is just broadcasting all the time the latest train position. And once we have the train position, we estimate how long the network latency is and just simulate the train position slightly ahead of the position we got. And it works well enough. If there's any hiccup, it'll be corrected by the next update of train position coming from the server. So there's no worry of desyncs there because if there was a desync, it's corrected half a second later. Okay. That was networking. How about rendering? So as I mentioned earlier, rendering is done using WebGL. Specifically, there's a package in the Elm ecosystem called Elm Explorations WebGL. The advantage this has over just doing direct browser API calls for WebGL, it's type safe, and also it's much easier to use. So specifically what I mean by that is normally when you're doing WebGL, or just OpenGL in general really, you need to be very careful about how you're setting up buffers. You need to compile your own GLSL programs. Those are your shaders for drawing things. You need to make sure the data and your attributes and your buffers and your frame buffers and all that sort of stuff is of the correct format for what your shader expects. And if you do any of this wrong, just about anything wrong, you'll get a blank screen and with a cryptic error message, and you'll need to spend a while Googling and scratching your head before you figure out what's going wrong. In contrast then, the Elm Explorations WebGL package, because it's type safe, if I try to pass in data to a shader and the types don't match, it's a compiler error. So it's caught immediately, and Elm is notable for having very good error messages. And that is the case here as well. On top of that, so the funny thing is Elm is known for being a very simple language. It has similarities to Haskell and like surface level details, but it's much more like its syntax is much more simple. But despite having a simple syntax, Elm does have built-in GLSL support, which is to say you can write your own WebGL shaders inline in your Elm code. There's a special notation for the start and end of your shader, and then inside of that is just normal WebGL shader code. So this is, I don't know, I find it a little ironic that Elm's a simple syntax, but it also has this, but I'm not complaining because it's enormously helpful here. Yeah, so with all of this available, it's pretty straightforward to put together a game using Elm that uses WebGL. Another thing, because this is Elm and everything's pure functions, the way that this works, in normal WebGL, it's extremely stateful. You have lots of different flags you're setting, and you're responsible for making sure the flags, and by flags I mean like Boolean values, like on-off switches for various attributes, they're set the way you expected. And it's very easy to like forget that, oops, this piece of code, it sets like depth checking to being disabled, and other code elsewhere is expecting it to be enabled. And now I'm wondering, why are my triangles rendering through each other like I have X-ray vision? In contrast, the WebGL package for Elm, you define up how things are drawn in a declarative way, and then the package itself figures out how to efficiently enable and disable flags to do what you expect it to do. So yeah, all really handy stuff. Okay, but more concretely then, in context of this game, the way rendering is done, we have the tiles, so like the fence around the cow, for example, or the houses that you saw earlier. Those are all what I refer to as tiles. and they're rendered in 16 by 16 chunks. This is for performance reasons. If, for example, instead I was just drawing everything visible on screen all as one giant mesh, and by mesh I mean like vertices, triangles. If I did that, then as soon as I move the camera, I need to redraw everything, which is slow. So I'm doing a tile-based approach where I have 16 by 16 tiles. When new tiles are needed to be shown, then I create that 16 by 16 tile, but then after that I can cache it, and tiles that are no longer visible are removed. In Town Collab, everything is a quad. So rectangles, essentially, 2 triangles fixed together like that. And then within the quad, I use a texture lookup to draw the various images you see. So the sprites, as they're referred to as. And all the sprites are on a single giant image, so that's what's referred to as a texture atlas. And actually, I can show you real quick what that looks like if I just go back to the browser view. Here's all the textures, all the sprites that can be shown in the game. So, for example, we were just looking at the fence, and if I zoom in a bit, there's the fence, there's the cow. You might be wondering, wasn't the cow black and white? What's going on with the cow here? And so that's the one thing I do in this game, is that there are a very specific shade of magenta and cyan, and various shades of those 2 colors that are swapped out while the game is running. And so these become user-defined colors. Essentially what I've done is I've written a WebGL shader, and I should have clarified earlier. By shader I mean it's a program that the GPU runs. So it's its own special language. And this program I've written then for the GPU, it looks at every pixel value in the texture, and if it sees this particular color, it says, oh, okay, I know. I swapped that out with a different color. And that's how then I can have the black and white cow here, and the fence is orange, not pure magenta. Likewise for the text, it's black here. Which, if you are very eagle-eyed, you might have realized at this point that the little hyphen or bullet point I have here, sorry, let me get back to main screen. The hyphen I have here, it's actually a bench. That's why I wanted to include this, because it makes the game much more flexible in what I can show without needing to literally draw all the pixel art for it. An exception to all of this, I just mentioned that everything's quads and a texture atlas. An exception to this is the map view. So I have this map you can also look at that gives you a more distant perspective, which is very useful on smaller screens like this one. It's still a work in progress. You might notice that there's the black pixels and the green pixels in the center, the dark green pixels, but then they kind of vanish on the rest of the map, and that's because while I can show the mountain range and I can show where all the water is automatically, because it's just it's using simplex noise to generate the geography. The actual tiles being placed, I only know about the tiles that are loaded within my nearby position. So there's nothing else to show. That's why the black and the green, which represent nature and buildings and such, are not shown elsewhere. Still a work in progress. If I hadn't mentioned that before, this game is still a work in progress. Anyway. Because we're using WebGL, and specifically because I'm using WebGL not only for what you're seeing here, but all the UI as well, I can achieve what I like to call the zero DOM experience. The advantage with this, or I should clarify first what I mean. If I just open up the browser window here and I look at elements, there's a canvas, and that's it. I mean, you have all the other standard stuff, but the canvas is responsible for drawing everything you see. The advantage of this is that I have full control, and I have full control over both how the UI looks and how it feels. This is really helpful with games where you're, like if you're making a typical website, you just want it to look like a typical website. But games, you typically want to have your own look. On top of that, I don't want to worry about like, oh, the game looks fine on Chrome, but on Safari, no, there's some bug, and now it's broken over there. There is still that with other things like audio APIs and whatnot, and also WebGL has slight variations. I forgot to mention that earlier. There is one very annoying variation between browsers, which is that when you load a texture, sometimes the default settings for how the texture loads is different between browsers. And so some browsers think it's okay idea to just mess with the colors a little in my texture, which would be unnoticeable in most cases, except, you know, I just mentioned that thing where I need a very specific version of magenta to swap it out. And so I had some friends asking me, hey, your game's kind of cool, but why is everything purple? Like, oh, and it took forever to debug that one. Sorry, a bit of a tangent. Anyway, so yeah, having full control over the UI is really nice for making games. But it does have some disadvantages. So accessibility is a big one. I do have keyboard navigation built in, so you can jump between buttons using Tab and Shift Tab. But in general, it's not as good as a typical website would be. Like even a website where the developers have put no thought into accessibility, the browser can look at the DOM and figure out how someone using a screen reader, for example, ought to see the website. And in my case, what DOM? So the screen readers can't do anything. I think in this case, it's a bit more okay because it's a game. Everything's very graphical anyway, so a screen reader I don't think would be appropriate. But it is, you know, a concern, and especially why this is not something that's done everywhere. Though I should note, I think there's a number of Rust crates, they're called, yes, Rust crates that do the same approach where they have a single canvas. But what they do is in the background, they also build up a DOM that's purely for screen readers to work around this. So I could do that, but again, making a game, that's not exactly the focus. Another disadvantage is throughput. So because I'm doing all the DOM-related computations myself, it's just slower because I'm going through JavaScript, and at the end of the day, Elm's compiling the JavaScript's running on this, and it's not as fast as the very carefully fine-tuned coded C++ or Rust that the browser's running in. But on the other hand, a typical website is built with throughput in mind and not latency. So for games, because I'm building something that's designed to render 60 frames per second, latency is a much greater concern. And so by doing it in WebGL, I can have a very low latency. And so I don't need to worry about like trying to do some kind of animation and the game is stuttering because, oh, there was a garbage collection or a layout computation that just happened. So yeah, I'm moving on. Okay, I just talked about this UI a whole bunch. What does it actually look like? Well, you saw it a little bit earlier, but I'm going to show it in more detail now. So I was earlier in presentation mode. Now I'm in the mode that a typical user would see. So down at the bottom here is just all the possible tiles that can be placed. So for example, I could pick the brick house and I could stick it here. Or I could go over to this little text input in the bottom right and I can decide that, you know, red is such a stereotypical brick house color. Let's go for, let's go for purple, or maybe that's magenta. So yeah, magenta house, looking good. And yeah, you just mess around. There's no real objectives. You just build whatever you want to build. You can place text as well and say, howdy. There's, you know, a settings page. Mine looks a little different because I'm the admin. And you can like invite friends to join. Over here in the top right, it's a little like well, it's a little hard to see now with all the tiles below it, but it's a invite tree. So it shows the root user, which is me, and then everyone I've invited, and then everyone they've invited, and so forth. Yeah, so that's the general idea. And that about wraps up what I wanted to talk about here. But one more thing that I couldn't really fit in, but I really want to show. So one thing this game supports is sending mail to each other. So over here, we have this building that says test user. So this person named test user, this is their post office. And the orange flag here, that means they have a letter that they want to send. And I happen to know it's a letter they want to send to me. So I can click on this train here to get it to head out. And it'll stop at their post office and pick up a entire wagon for this single letter. And then it'll reach my place. And I got the letter. Oh boy. So I'm going to click on that now. And you see here, I have lots of other letters. We're going to ignore those. But I can click on the new one. And that's all, folks. The URL at the bottom, if you're interested, you can look at all the slides. If you go to this URL here, there's a 0 at the end there. Don't miss the 0. It's a little hard to see. I couldn't fit the whole URL in the mail. But yes, that's all, folks. Thank you.
Thank you very much, Martin. Very, very cool. And as always, I'll start by saying we'll share the link below in the...
That might be easier.
in the description here. So if you're watching this in retrospect, the link is in the description. We'll also share it on the MeetUp page, so people can come and click. Spontaneous question: have you ever thought like gathering a group of friends and just sitting around and doing stuff and sharing everything on a big screen? Or maybe you've already done that. It seems like the obvious game, you know.
Yeah.
Invite your friends, pop a beer, and just draw away.
Yeah, I have gotten some friends together. I think we were like a group of, I don't know, 6 people. We had like 3 sessions. And yeah, it was fun. It's like, it's a certain type of person who would enjoy this game, because I'm certain a lot of people want games that are more focused on something rather than just placing tiles. But, well, if you liked Lego or Lego Loco, that old game, then I think you'll enjoy this as well.
Cool. You also said no Doom. It's really, I've seen another, we have had other presentations here on this meetup around Elm, and no Doom, no JavaScript. It seems really interesting, as I've been working sometimes with JavaScript and so on. Are there more work with WebGL instead of throwing out the Doom and then getting into WebGL? Is it more work for you? Is it more work as a developer to get it to work? And
certainly reaching Hello World status takes a lot more work, even with this Elm package that simplifies things. Just text in general is something that's quite difficult when you're doing WebGL. As an indication of that, when you're doing WebGL, the first thing you'll typically do is not called Hello World, it's called Hello Triangle. And it's drawing a rainbow, well, not quite rainbow, it's a triangle with a green, a blue, and a red point, color blending between them. To get to the point where you have text, you need to load in a texture. You need to make your own shader that reads from that texture. You need to make sure the quad you've created to draw that texture on is lined up correctly, so it's not stretched horribly, or it also needs to be lined up with the device pixels on your screen. So typically when you're a web developer, you're thinking in terms of CSX pixels. So you're not worried about, when you think pixel, typically you think of a pixel that's larger than the actual physical pixel. For example, when you're on your smartphone, like you might think, oh, my smartphone is 375 pixels wide. That's not true, actually. It's wider than that, but the pixels have been like compressed. Multiple pixels are in a single CSX pixel, because you don't want the UI to be if the text was 12-point font with device pixel size, it would be tiny. So this is what they do to accommodate that. So you don't need to think about it normally. But with WebGL, you do. If you don't account for this, everything's blurry. So there's lots of stuff like that. But once you have it set up, then, yeah, it's actually kind of easier, because there's so much, filling with the DOM you don't need to worry about.
Cool. I have a question. I think you mentioned it last time that you were that there was no way to load assets on demand, and everything must be loaded up front.
Are they referring to the previous presentation I gave here?
Maybe.
Okay.
Yeah.
That's not quite true. And I should clarify, the Elm Explorations WebGL package has some limitations around what you can do. It is trickier to load textures and meshes on demand, specifically because there is no real good way to unload meshes and textures at this point. The way it works at the moment is you wait for the garbage collector to just notice, oh, well, you don't have a reference to that buffer ID anymore. And then in the background, there's a weak table that's also holding a reference to that buffer ID. And when it sees the buffer ID is released from memory, it goes to the GPU and tells it, okay, you can release that memory. But garbage collectors being what they are, you cannot rely on this happening in a timely manner. So I think that's might have been what I was talking about last time.
Cool. Another question: are you in your daytime job? Are you working with Elm, or are you working with other like JavaScript, like a lot of people?
Oh, I can do one better than working with Elm. I'm working with Elm and Lamdera.
Oh, cool.
So at my day job, actually, I'm working at a company called Ambu, and it's a UK company.
Yep.
We're working with helping people insulate their homes.
Oh.
And specifically, my job then is to make a web app that lets people view their house as a 3D model. So we have a floor plan of their house. And so my job is to parse that floor plan. The format's called IFC and is the most object-oriented 30 years ago format.
Of course.
But once that's parsed, then 3D model of that with a viewer. So it's a lot of WebGL and Elm and Lamdera in my day job too. So I'm very happy about that.
I'm gonna ask you the same question. Do you feel you have is it easy to recruit people?
So at Ambu,
people, or maybe you don't need to find people.
So at Ambu, I've not worked there too long. We haven't had a need to hire any more programmers yet. I suspect we won't need to hire any for a while. But my impression from past jobs is that as a Elm programmer, it's hard to find jobs. As a Elm employer, it's very easy. Yeah. Which, happy for the employers out there.
Exactly. All employers, listen. Yeah. It's easier to find functional programmers.
Just write a message in Elm Slack if you want to hire someone.
Okay. Here you go. Yes. I have no more questions. Again, thank you very much for your presentation.
Thank you for having me.
You're welcome, and you will be welcome again if you want to present more. With that said, everyone, thanks for tonight. And as always, if you or someone you know should present, just reach out to me. You'll find me on MeetUp, LinkedIn, Twitter, wherever. Just reach out to me, and we'll put you on stage. With that, thank you very much, and have a nice evening, everyone. Bye.